Okay, good. Thank you very much. First, I'd like to thank the organizer for inviting me and to give this talk. My assignment is really to tell you the physics at the electron-ion colliders. And it has been a really long journey over definitely more than 10 years, a lot more than 10 years, for the nuclear physics community and also the funding agencies to come together to reach its decision to go ahead to build US-based electron-ion colliders. So quickly, just like in the high energy physics, there's a snow mass series to decide what the future plan. In the nuclear physics, there is a long-range plan process for every 5 or 7 years. Then really for EIC, started very first to say 2007, this long-range plan clearly say this is the most very, very important things to build. Then after that, there was a Institute of Nuclear Physics program to study all the physics and details. Most important milestone in the whole journey is this release of the electron-ion collider white paper from the community, organized by both Brookhaven and Jefferson Lab management. You have a committee to produce a community-wide document to set the science case without worrying too much detail of the politics between the two labs which are competing for the machine. So after that, there was next long-range plan, 2015, as a community state very clearly, this has a highest priority to build after the FRIP completions. Then immediately follow that DOE asked the National Academy of Science to detailed assessment of the science of the electron-ion collider. In 2018, the National Academy of Science Committee released its report, say this machine will answer science questions that are compelling, fundamental, and timely, and help maintain US scientific leadership in nuclear physics. They identify 3 profound questions. How does the mass of nucleon arise? How does the spin of nucleon arise? And what are the emerging property of dense system of the gluons? So at the beginning of this year, the US DOE announced its selection of Brookhaven National Lab as a site for the electron-ion colliders. This really represents the start, a new era to explore the emerging phenomena of QCD. So quickly, the structure of this new winning design from Brookhaven is based on the RIC infant structure. Instead of the RIC have a 2 heavy ion or proton beam line, they will add the electron line to have electron-ion colliders. The most important thing for electron-ion collider is a set of parameters required for the machine. Because as a white paper clearly stated, if you want to have a machine to reach the new frontier of QCD, you have to achieve these parameters or better. So the parameter is defined, the center of mass energy is around the 20 GeV to 140 GeV, actually 100 GeV that can be reached to 140 GeV. And our key is the required luminosity, 10 to 33 to 34. And also require the hadron beam polarizations as well as electron beam polarizations, and also require the ion species for the hadron part from a proton all the way to uranium. I will tell you in my talk why all those parameters are very, very important. Will help this machine to do something no other machine can ever do, and also require up to 2 interaction points. So for the rest of my talk, I will first emphasize briefly the frontier of QCD is strong interaction. That's why we need to spend this money to build this machine. And I re-emphasize the QCD at the Fermi scales, which is leading to a new sort of scientific field called nuclear Femtography. And why do we need electron-ion collider? And I really emphasize what the EIC can do, but why other machines cannot do even with the upgrade. So the frontier of QCD, I put in the 2 quick categories. One is really QCD at high temperatures, especially that connected to the early universe, because at that time, there was no human, no proton, no neutrons. We'd really like to understand where do we come from? how the hadrons emerge from quarks and gluons. We do have facilities, relatively heavy ion colliders. Then you have SPS, early days, then RIC, and then of course LHC. So another important part of frontier of the QCD is really to understand ourselves. What are we made of? In the sense to understand a visible world at 3 Kelvin degrees. In that case, you like to understand what is the internal structure and the dynamics of hadrons, and how did the hadrons emerge from quarks and gluons? How does a glue bind us all? Then what's the facility I will emphasize for the future is the electron-ion colliders. We try to search for answers to these questions at the Fermi scales. What is the QCD at the Fermi scale? Why it's so special? QCD has a number of defining properties. Probably the most important one is the color confinement. We do not see any quarks gluon in isolations. So it's very difficult to define or even quantify the structure or internal structure of nucleon and nuclei, which are the emerging property of QCD. So then those are property corresponding to really the landscape of the QCD around the Fermis. Then we know that from one end is a color confinement. Then we have a nucleon and a nuclei. On the other end, we have another property of a QCD known as asymptotic freedom. I will talk a lot about it, which is great. Without that, we could not really test QCD at the short distance as we have been achieved. But we learned a lot in this region. LHC physics help us to clear up a lot of issues of QCD in the asymptotic region. But however, the complexity and the richness of QCD are in the region between the asymptotic freedom, meaning that, say, 10 to minus 1 Fermi, all the way to the size of a nuclei, say 10 Fermi. These 2 order magnitude really define the QCD at the Fermi scales. The most interesting, rich, and complex region of the theory, all emerging phenomena actually depend on the scale at which we probe them. Then the QCD asymptotic freedom is not only a great defining property of QCD, help us to test the QCD, give us all the confidence about QCD dynamics in the asymptotic region. Then, and also most important is that because the force of the strong interaction becomes weaker at the shorter distance, which give us a really controllable probes. Because we never see the quarks going in isolation. How can we see them? How can we probe them? How can we control the probes? It is because of asymptotic freedom. So it allows us to explore the structure of the nuclei indirectly by using local and sharp and then control probes. Then when we talk about hadron structure, that's a focus, emphasis of the EIC. Then we often think about structure like a still picture. We know that from the crystal structure, the nanomaterial, even goes all the way down to atomic structure. You have a core of a nucleus. Now you have very clear, it's a picture in the popular magazine, say quantum orbit. All this picture is possible because the motion of nuclei is so slow compared to the speed of light, and also the photons are neutral. But none of these concepts, when we talk about structure, will not work for the strong interactions because now, especially no still picture for hadronic internal structures. Quarks gluons are moving relativistically. Color is fully entangled. I gave a simple example like a B meson. You can say probably most like the hydrogen atom. You have a very heavy core, a B quark. Maybe a light anti-quark moving around just like a hydrogen electron. For the hydrogen atom, the answer is no. You never have a clear quantum orbit because the gluon carry color. You have really the brown mugs that have all the quantum fluctuation around the B meson. So how you define the platonic structure, how you see them, define them, then actually everything we measure in the strong interaction at this proton level is the quantum probabilities. In a sense, it's a matrix element of the hadron of the quark and the gluon fields. So the question is how you see it. You never see the quarks and gluon. The most important concept, I think the tool to match what happened at the proton level and what happened at the hadron level is known as factorizations. The idea is that if you have scattering between the electron and proton, the simplest case, you'd calculate scattering amplitude and square to get a cross section. But because we cannot calculate anything at a proton level directly, so that you don't know the scattering amplitude fully, so how can you get a cross sections? Luckily, because the strong interaction, the collision is so localized, you can square the hot collision part as a protonic part. You can calculate perturbatively the interaction between the protonic collision part and the dynamics happened at the hadron level is powerfully suppressed. So in that case, you can actually, as approximation, you can replace this non-perturbative calculable cross-section as a product of two probabilities. One is known as the hard part. You can continue to improve it by perturbative calculation in the higher order or sum of the logarithm. Then whatever corresponding matrix element give you the information of the proton inside the hadrons. Now, of course, this approximation, there is an uncertainty, that's the power correction. The controlling this part is very, very important to make the precision predictions. How successful this formula? We heard all this wonderful talk already in this workshop on the LHC physics. I use one example. People use all these different channels to connect the proton in the LHC collisions, which is a non-perturbative. Then you put them together in terms of factorization, cover all the kinematics from X and the Q squares, then try to see if the theory from a QCD perturbation theory calculate the hot part, and if you can extract a uniform or the universal set of proton distributions, then the answer is yes. So then we find that if you're leading order calculate, you have a chi-square is larger than order of 1. But when you go to next leading order, you will find the chi-square for all the data set compared with the theory, and the one set universal proton distribution is very much close to 1. So the conclusion is that with all these different channels, the standard model, electric weak process plus QCD perturbation theory, and the one set of universal non-perturbative PDF works at the LHC physics at the asymptotic regime. However, I want to emphasize we need a new type of probes for 3D hadron structure, internal structure. The reason is when you have a single hard scale, it is too localized. It does pin down the particle nature of the quarks gluon, but it's not sensitive to detailed structure of the hadron at the Fermi scale. So imagine you want to understand confinement. You understand how the quarks, the gluon confine the move inside the hadron. What is the distribution of probability to find the quarks gluon at the sufficient point inside the hadron? Since the collision is so localized, the point is so small, you should be able to have more information on the detail of the protonic structures. But a single hot scattering is not sensitive on the detail of these structures. So we need a new type. The idea is you need a probe, still hot, but you need a two-scale probers. One scale is so large to localize particle nature of the quarks gluons. At the same time, you like to have a natural second scale, the Q2, which is sensitive to the scale of the Fermi. So that gives you a chance to see the internal structure of the quarks gluons. And also ideally, you like to hit the hadron so hard, but without breaking it. But once I will emphasize next slide, once you break a proton, like in the LHC, you generate a lot of shower. You mix the structure information with the collision information. That's the information I want to emphasize. So it's really the unprecedented challenge to really separate the collision effect from two hadron structures. Take the simple example, you heard the Higgs production of any Joyon type of process. You have hadron-hadron collision, produce a heavy particle with the transverse momentum certainly much less than the mass. So you do have two scale observable. However, because you break with the proton, then you realize you generate a tremendous showers. So the particle transverse motion PT at the collision point you measure is not the same as the transverse momentum PT in the hadron wave function of the hadron structures. So how can you control this part? This part is often characterized as QCD evolution when you change the scale. But actually, when you go to high energy, I will show you the shower is dominated by perturbed effect rather than non-perturbed things, then you wash out this non-perturbed effect. I gave a simple example, a paper I wrote a long time ago with my collaborator Ed Berger. The structure could be easily washed out in a high energy collision, a Higgs production at LHC. Because every radiation is soft, so we like to calculate the impact parameter space, Fourier transform B space. So the factorized cross-section is proportional to distribution, not in terms of KT, but in terms of impact parameter B after Fourier transform. So the final observed spectrum is the Fourier transform, the B space distribution. You will find at LHC for the Higgs production, after this energy and the mass, you will find the B space distribution is completely dominated by small b regions. Even though you go all the way to infinity, but tail is so small, the non-perturbed effect is completely washed out. So then we can predict the PT spectrum of the Higgs production with really confidence. Even with all the scale choice, you have uncertainty, we're pretty much confident what the PT spectrum is. This is exactly the basis now you can do the say soft collinear effective theory. You can sum all the logarithm, get a precision measurement, because all the non-perturbed things in a sense is strongly suppressed. So that example tells you it's a wonderful for this process to test the things at the LHC, but it's a terrible for our interested to study the structures. Well, the question is, if we want to structure, we really like to have a control at the low energy scales. So then also I want to emphasize, so why we need EIC? We have a lot of hadron colliders. We have E plus minus. Well, it's a great machine to study the emergence of the hadron from proton, from energy, because you start with no hadrons. So it's not ideal for the hadron structures. And LHC, of course, has lots of data. You start with hadron, but unfortunately, colliding hadron most likely broken. Once it's broken, the shower dominates the transverse information, or you lost all the information on the imaging. So it's a very, very difficult process. On the other hand, if you use lepton-hadron colliders, in that case, because you have a controlled scatter leptons, you really have a hadron actually can be broken as well as stay intact, as I mentioned to explain to you why, because that's another important discovery from HERA. Then we find that you can image the protonic structure, you have a hot scale, and also you can control the leptonic scattering plane by observing the final hadronic state. You have a hadronic scattering plane. By the angular modulation of those two planes, you can run a lot of the spin property and the intermediate state you produce. So that's why lepton-hadron collider is very unique for studying the hadron structures. So that this is the process, it's a facility, a single facility like a new generation Rutherford experiment. Instead of the alpha particle, you have electrons. You have a controlled probe as a virtual photon, and also you can either break or not break the hadron. You can measure inclusive process. You can only measure the scattered electron, nothing else. Even that, like a Rutherford experiment, you can learn a lot. And also with the collider, you can easily measure the final state particles. Then you can do a semi-inclusive process, introduce the two scale, the Hall scale, as well as the second scale, I need to tell you. As well, you can do the exclusive process. You can hit the proton very, very hard without breaking it. You can really see the imaging. So then also why EIC could do something HERA could not do. We had a HERA for 15 years. Well, you can do the quantum imaging. HERA discovered 15% of the time EP events are diffractive, protons stay intact. But unfortunately, they didn't have enough rate, enough event to do the analysis. US-EIC required 100 times to 1,000 times luminosity, which is a critical than the HERA. It's a critical for the 3D images. And also see the quantum interference. We know every single cross-section is the probability you have a quantum theory underneath of it. So to see the direct quantum interference, you need another knob, another observable. For example, if you have a spin, a polarized one, you measure cross-section, you can should be some of all the amplitude, same initial state and final state, and square them. Now, when you take a different cross-section with the spin flip, the first turn dominated by single hadron production is independent of the single spin because of QCD, the vector interaction, preserve the helicity. You will find that a symmetry is directly corresponding to quantum interference between first two. Then you measure quantum correlations. You can change the helicity from the amplitude to circumscribed amplitude by the composite state, core-gluon composite state. And also use having nuclei, we know that you can you actually have an advantage you never can imagine in the high energy scattering, because quarks, gluon, all the hydronization take place at the Fermi scales. We never have detector at the Fermi scale. We cannot see any quarks in the modern detectors. How can we have really better control, understand the quantum, the color neutralization and the emergence of hadron with the nucleus as the detectors? Nucleus is a controllable new detectors. So then EIC summarized quickly one slide, popular one is probably the Bishop's CT machine, not in the way in the hospital, but it's a way in the laboratory to cascade the proton at the Fermi scales. And also you can have the machine really can break the proton and nuclei, try to see the internal structure to study the quantum entanglement. So now finally, I use a few examples to tell you why this machine is unique. So then as first a simple example, how do we study the emergence of hadron, have control the detector. We use the nucleus, as I mentioned, as a Fermi scale detector. You do the scattering, you can control the photon, you know, the kinematics of scattering leptons. Then you try to understand and produce a hadron in the final state. All the quarks will have to go through nuclear media, they have interaction in the colors. So we simulations say, if you do look at the pion, no matter what kind of model you have, you always have a suppression. But if you look at heavy particle, D meson, or even the B meson, which is very rare at the EIC energies, then you will see the characteristic different than enhancement. The reason is the hydronization. D meson is have the peak in the highest compared to monotonic 4, the pion hydronization. Then you will, because the shift in momentum scales by radiation, then you will see actually the enhancement in certain regions. And also another thing addressed, what's a mass? Mass is a very, very important point, because Higgs magnetism generate all the mass, but it's not enough for the hadron mass. It's very, very tiny. Then we know from the lattice calculation with a few input parameter, we can calculate mass spectrum to a very, very good accuracy. That means the QCD does generate hadron mass. The question is how the quarks and gluons generate them, how to quantify them. Then, so one of the examples is what's a mass? Mass is the energy of the particle when the particle is at rest. You can take the scale invariant case, take a trace energy momentum tensor, then sandwich it between the proton state. That will be the mass square proportional to. Then you will find that from QC, there is a trace anomaly term, purely quantum effect, and also Carl symmetry breakdown related to having a mass. So, and also you can study these. If you can measure this independently, you can test it. But so far, it's difficult to measure this one. And also you can decompose them into, say, energy momentum tensor at 0, component, that's the energy, if you project it into the proton at the rest. So you can write it into the form, into the quark energy term, operator, gluon energy term, and the Carl symmetry breakdown and trace anomalies. So the key is, like every sum rules, if they're useful, if only individual term can be measured independently. So one of the key difficulty to test this is this quantum anomaly. There's a lot of work I've been going on to understand how you can measure from a controlled photons, virtual photon probe, and measure the heavy flavor in the final state. In principle, exchange of vacuum quantum number have a lot of gluons. But however, if the probe is so localized, maybe dominated by 2 gluons, and maybe you can find it eventually have a connection to the anomaly. This is really universal effort. There has been a lot of workshop going on. So it's a really effort people really putting into it. But also another major quantity is the spin related to National Academy of Science report is we know the spin half, which is angular momentum of the particle when the particle is at rest. But if you put into the probe, if you have harmonic collision, you have holistic contributions, meaning the spin coming from the property individual particles, as well as the motion, orbital motion part. So far, after 30 years effort, we learned a lot of the quark helicity is about 30%, and the gluon it's about 40% in the region we measured from RIC data. But for orbital motion, we really don't know. We just started. We have to understand transverse motion of quarks, gluon inside the hadrons. This is the trends you can see from early measurement. You can start to see, but the error bars are huge. We don't know exactly. So really to answer these questions, we need the EIC. EIC not only can pin down individual flavors to the distribution, a much smaller error, integrate, give the holistic contributions, but also you can most importantly combine with the RIC data, or not combine with the JLab data, it's good for larger X variance region, as well as the EIC, you can see the error, even though we don't know the central value, but the error for delta Q, for the quark contribution and the gluon contribution is so small, you can really move this central value by the EIC, but you know the uncertainty is sufficiently small, give us a really confidence to understand whether there is a motion and the property, how they contribute to this emerging property of the hadrons that I explained. So we need to understand the transverse motion. This is related to the last topic I want to emphasize is the TMD and GPDs. So you need a true scale observable to see internal structures. That means you have to, but it's in the lepton hadron collision is very, very natural. If you look at the semi-inclusive process in a photon hadron frame, the hadron you produce or jet you produce have a very small transverse momentum compared to the Hall scale. So naturally, you can be sensitive to confined motion. They are encoded into the transverse momentum dependent proton distributions. And also in the exclusive process, measure, say, a photon or quarkonium, but measure everything with the protons slightly deflected. In this case, the scale, the Q square is much larger than T. Then again, the two scales, the Fourier transform T give you the imaging information of the space. Then also, why this, but there are lots of functions once you open up a transverse momentum, but because you have a two scale and a two plane, you have a leptonic plane and a hadronic plane, the angular modulation will help you to separate the TMDs. The hadronic process, it's almost impossible to do it. Then the theory part is very, very important because you need the solid theory to match what happened in the short distance Hall part and what happened in the hadron colliders. So in this case, theory is from the 5-dimensional Wigner functions, connected if you the TMD, if I integrate the transfer position and integrate the momentum, get to the sort of GPDs that generalized proton distribution give a special distributions. Now, I'll give you one example. Then for this semi-inclusive DIS, dependent kinematic variables, you measure the transverse moment of hadron for fixed Q square. Now you will find when the QT is PT is much less than Q, you have a TMD factorization is well proved. And when the PT is the order Q, the collinear factorization, they have a smooth link between them. And also when you integrate the PT, then you have, again, the collinear factorization, it's a single scale. Then also you have very high PT, then you, in the sense, you have a single scale, but it's a two scale, but it's a different type of summation. So theories works is very well. So then the physics behind it, why we do that? Because of the transverse motion is the fundamental information we'd like to know to understand the confinement, and also give us a very first measurement of quantum correlation between this a property of a hadron, the polarization of the hadron, and the motion of the proton. Because you measure, when you have the collision, you measure a particle come out the left-hand side, right-hand side, they're not the same. The example you can say TMD as a simulation, if it's an unpolarized one, spherical symmetric in transverse direction. If you polarize, you will find the proton has a preference moving in a certain direction. When you have a collision, the particle come out, we have a different direction. So that's from initial state. Similarly, for the final state, if you know the direction of the quark polarized. So then finally, the DVCS, the imaging, you measure the transverse momentum distribution of the particle, you Fourier transform, get this distribution in the B space. From this thing, you can actually define the proton radius of the quark distributions instead of just the electromagnetic charge distribution. You can do the same thing for the gluons. You can measure distribution. You can have a proton radius of the gluon distributions. Then the physics behind the very, very important, tells you how the quarks gluon are confined inside, the behavior of the distribution, how fast they fall, they depend on QCD mechanism, and how far the tail lasts will really also depend on QCD and will affect the nuclear force. So the very fast last one quickly is that how QCD hold us together to control the nuclear force. We know at the HERA trough, at the small x, gluon density goes like crazy, like LGC, you need only the glue-gluon fusion to dominate most of the process. But when the density or occupation maneuver close to 1, gluon will recombine. So that's exactly the probe at the small x is not localized. If you look at it in the hadron frame, the particle coming, it's really the photon quantum fracture QQ bar pair, they can interact with the medium, not only the nucleon with one nucleon or two nucleon, any number of nucleon, that depends on the color correlation inside the nucleus. The simple question is, we know the nuclear landscape or nuclear force is not the same as simple nucleon superposition of nucleon landscape. The simple question, but it's a very fundamental. What does the nucleus look like if we only see quarks and gluons? Does the color of nucleon A know the color of nucleon B? So if the answer is yes, how can we test that? If the answer is no, it's EIC can tell. So that to close this, I use a very simple experiment, day one experiment. So do the same measurement on the heavy nuclear, on the Duron, the ratio, the simple structure function. This is the data we have so far. Stopped here. So the question is, when this point goes the small x where the EIC can reach, the question is, does that curve goes to the flat? If they go flat, that means geometrical structure factor, that means the color completely separate, localized inside the nucleon. If they go continue fall down, the long range color correlation, nucleus acting could be increasing, even act like a bigger proton. Though there's a color leak outside the side of the nucleon, it's a simple measurement, EIC can tell. Let me summarize that this is really the international effort. There are a lot of over 1,000 collaborators, EIC users group already, and running out of time. Let me put on my conclusion. I'd like to thank everyone for listening. Thank you.
Thank you, Jianwei. That's a very nice talk on the EIC program overview. So we do have 2 questions in the Q&A. The first question from Alex Petrov. Are there plans to study new physics at the EIC? For example, the flavor validatings like E with nucleons and goes to mu on top or something else.
Yes,
are there plans for those?
Yes, absolutely. Because of the time, I could not include those in it. Their working group exactly studied that, especially in the Tor channel. It's very promising, interesting.
Okay, cool. And the second question is from Carlos Wagner. In presenting the contribution to the proton mass, you decompose in several components. Can you show that slide again and explain the exact meaning of each term and how they can be measured?
Yes, the first term is, first term is related to so-called quark energy, related to the proton energy. Then they can measure it in the momentum distribution of the quarks inside proton. Next, the gluon energy. Then next 2 is like the one I showed in the first early part of that slides related to trace anomaly and the chiral symmetry break-ins. The chiral symmetry break-in, Lattice has done a good job getting closer and closer, even that, but still have issues. Then we try to calculation, it's like a sigma term. People try to use effective theory to help to get that. Then the most difficult part of the trace anomaly. Trace anomaly, it's the gluon sector. It's a very difficult, it's twist 4 operator. It's difficult to calculate on the lattice. And also we have been working very hard, many group of people work on it, try to see whether or not under controllable approximation, we can measure through experiment measurement. As the example I gave below.